Okay, now we're talking about elastic and inelastic collisions. Now, collisions, immediately you think of momentum, conservation of momentum, force, and impulse should be the things you're thinking about. Now, an elastic collision, the elastic collisions are the bouncy collisions. They're the things that are hitting and bouncing off each other. Ideal gases are considered to be a perfectly elastic collision. The closest we can come on Earth is something like billiard balls, pool balls on a pool table, something like that, bouncing off each other, not much energy lost, hopefully none. Momentum is conserved, and momentum is conserved in all collisions, and that's your starting point in any collision thing. But if the word elastic is put in there, what that means then is kinetic energy is also conserved. So now I have two things that are conserved, so therefore I can have two unknowns. Now an inelastic collision is obviously the opposite of that. They're the ones where things stick and slide together. For example, slide tackle in soccer, somebody hitting a catcher in softball, things like that. Car crashes where the cars hook together and slide together. They oftentimes, like a good example problem is when they have train cars coupled together so they roll off at the same speed, things like that. Ballistic pendulums, how they find out the speed of bullets, are also inelastic collisions because it's embedded in the block of wood. Momentum is conserved. It is still a collision. That hasn't changed. The difference is kinetic energy is lost. It's converted into something else. A lost is a bit of a misnomer. A perfectly inelastic collision means every bit of the kinetic energy is lost. In the real world, we live somewhere in the middle. Most of the time, nothing is perfect. So therefore, usually some of the kinetic energy is converted into light, heat, and sound. So it disappears. We have to really say that it's a perfectly elastic or perfectly inelastic collision. If they say elastic, you have to assume it's a perfectly elastic collision. So let's look at a problem. A 100 kilogram bumper car with a 50 kilogram teen moving at 5 meters per second hits a stationary 100 kilogram car with a 100 kilogram adult in an elastic collision. What is the final speed of each car? Now, we know that momentum is conserved. It's a collision. They throw in the word elastic, so that means kinetic energy is also conserved. Now, that's going to allow me to get two equations, two unknowns, two equations. That's how we're going to solve it. Now, the algebra gets a little sticky. At the AP level, they would probably not expect you to do an entire one of these by itself. But let's go through one. It's good practice. So first of all, for momentum, let's draw a momentum table. Our objects are the 150 kilogram car and the 200 kilogram car. And of course, we want to know the total. So when we draw the momentum table, we're going to list the momentum B before in the left column, the momentum after in the right column. So 150 times 5 for the first one is 750. The 200 kilogram car is not moving. It has no momentum. Our total beforehand is 750. Now afterwards, I'm still going to have 750 units of momentum. That doesn't change. The difference is, though, I need two velocities. They don't give me one of them, so therefore I'm going to have to leave it in equation form. So I'm going to go 150 times Vt. Vt would be the velocity of the teen car, and 200 times Va. Va is the velocity of the adult car. Now, since we know kinetic energy is conserved, I can draw a kinetic energy table. Now, if you need to stop right here and copy that table down, you can. And what I'm now going to do is try and fill in as much of that as I know. Well, I know the first one is 1/2 times mass times velocity squared, so it's 1,875. I took the mass of 150 kilograms and the velocity of 5 meters per second and plugged it into 1/2 mv squared. The 200 kilogram one is easy. It's not moving. So therefore I have 1875 units of kinetic energy beforehand. Those units would be joules. I also have 1875 units of joules afterwards. Now, I can't simplify those any, so if I go 1/2 m times vt squared, well, 1/2 of 150 is 75, so 75 v of the teen squared plus 100 va squared for the adult is equal to 1875. So let's go back to the momentum one and write an equation. 150 vt plus 200 va is equal to 750. It is best probably to drop the units until the final answer, because that way we can get everything to, it just makes it easier to look at. You do have to make sure your units agree, so if you have, you're going to need to have all kilograms and all meters and all seconds. You can't have one in kilograms and one in grams. If you do that, you have to convert one of the two units. Now, you can simplify that by dividing everything by 50. I get 3 VT plus 4 VA equals 15. Straightforward, simple equation. The kinetic energy equation, 75 VT squared plus 100 VA squared, is equal to 1875. I can simplify that a little bit by dividing by 25 just to make it a little bit lower. I get 3 VT squared plus 4 VA squared is equal to 75. Now, on the next page, I'm going to solve two equations and two unknowns. You can use any variety of methods to solve those. You have a graphing calculator. I would just use those to solve it. Use determinants or use any of the things you've done before. Graph the equations. You've done a lot more of that more recently in math. So you should be okay with that. Now I'm going to do it the substitution way. Now maybe I made an algebra mistake, but we'll take a look at it. So I start with my two equations at the top. What I'm going to do is start with the 3 VT equation, and I'm going to solve that for VT. So VT is equal to 15 minus 4 VA divided by 3. On the other side, I'm going to simplify it a little bit by moving the 4 VA squared to the other side. I'm going to plug in the value I just got for VT, and then I'm going to crunch my way through the algebra. I don't think I made an algebra mistake, but you can check it if you want. You reduce down to 5 VA squared minus 7.5 times VA minus 60.9 is equal to 0. Then using the quadratic, you get two choices for VA. VA is equal to negative 2.181 meters per second. That means the teen car bounces back, the adult car would go back towards the direction that the other car is moving, so that's probably not going to happen. So that's probably the choice that doesn't work. Or the velocity of the adult car can move at 4.32 meters per second. Now you can check both of your VTs by putting in each one of the values back to your VT equation originally. Check the math if you want. The answer, I think, is probably 4.32 meters per second and 0.76 meters per second, but there are two potential choices. The teen car is going to slow down, the adult car is going to move. And you can check my algebra. Now let's look at an inelastic collision. A 5 kilogram cat at rest is pounced on by a 3 kilogram cat moving at 2 meters per second. With what speed will they roll away if they stay tangled up? So you just have one cat jumping on another cat. It's what they do. We're going to draw a momentum table when we know momentum is conserved. We have a 5 kilogram cat, a 3 kilogram cat. Now for the 5 kilogram cat, the initial momentum is 0, sitting still. The other one is 3 times 2 for 6, so our total is 6. Well, I have to have 6 after the case. Now here's the key thing. If they stay tangled up, they're going to have the same final speed. So that value is going to be the same. So 5 times V, which is the momentum after for the 5 kilogram cat, plus 3 times V, again, they have the same speed, is going to equal 6. So therefore, V is equal to 6 divided by 8, 0.75. We're talking velocity, so it's meters per second. Hope this helped. Remember, elastic collisions are the bouncy type collisions. Kinetic energy is conserved. Inelastic are the stick and slide type collisions. Hope this helped.